Hi everyone, I'm Zdeněk. I hope that you have enjoyed the show so far, because I have. And so today's talk will be dedicated to improvements or code density improvements beyond the standard C extension. Before we dive into this topic, let me just briefly introduce our company, what we do, what we offer, what we have. So who is Codasip? Well, Codasip is a leading provider of a RISC-V processor IP. We have a family that's called Berkelium as a tribute to guys from Berkeley who invented the RISC-V in the first place. On top of that, we have also an EDA tool by which you can configure the BK family as whenever you want. And I have a slide on that later on. The company itself was founded in 2014 in Czech Republic. Now the headquarters in Munich in Germany. The R&D is based in the Czech Republic, and we have offices here in the US as well as in China, in Shanghai. We are founding member of RISC-V Foundation. We are a member of several working groups within the foundation, such as compliance and others. And because we are using some open source technology, we are actively contributing back whatever whenever we want or we can share with the community. Mainly the LLVM part, so LLVM, LLDB, or the OpenOCD and other tools or software tools that we are using. Now, if you look into BK family into more details, so all of them are ready, verified, tape-out quality. They have industry standard interfaces like AHB or XI. And more importantly, all of them are fully customizable if you need to do customization. We have a 3 basic starting points. So we have a BK3, which is the entry-level 32-bit core, 3-stage in order, simple pipeline, very efficient in terms of power and PPA in general. Then we have a BK5. It comes with 32-bit or 64-bit flavor. You can choose whatever you want. It's 5-stage machine. There's a prediction, optional cache. The cache is available in BK3 as well, by the way. And then last but not least is BK7. So BK7 is the biggest one. It's Linux capable core, 64-bit. MMU, page table walk, TLBs, whatever you have to have for Linux to be able to run on such a machine. You can configure the cores in a way that you can select the different letters, I would say, from the spec, such as IMC, IMCF, and so on. So these cores are configurable nicely. And if something is missing, then you can use our tools to add these missing pieces. So we can add some, DSP instructions, or as you will see in a minute, we can also add some compact instructions to help with the code density. So, you have to have some kind of tools to help you with this kind of customization, and this is what we have as well. So Studio comes with IP, and this is a set of tools that allows you to do modification of the RISC-V processor. The tool itself has been introduced in 2014, but is based on research that's more than a decade ago, started more than a decade ago. It's proven customers are using this tool to develop the RISC-V cores, so it's in use already. Studio stands on the language that we invented. It's called CODL. It's architecture description language by which you capture the ISA as well as the microarchitecture. So we capture the instructions such as ADD or branch instructions, and you can also capture the pipeline. So we can capture how many stages you have, how the fetch unit behaves, and so on. So that's captured in a CODL. CODL itself is not tied to any particular architecture or instructions. So you may describe simple bit manipulation instructions like we have in the bit extension, bit manip extension. You can also describe the SP extension that we have in the P extension, and you can go to vectors as well. So then, once you have this description, then you can go, you can click on the button, and you can obtain the RTL, which is Verilog, System Verilog, or VHDL. It's up to you, really. And then you have also SDK that's aware of extensions that you did in a code. The SDK itself is LLVM based. So currently we are based on the LLVM 8, I think, at the moment. We are also using a debugger from the LLVM project, so LLDB is there as well. We have a couple of C libraries, newlib, for instance, or some other libraries that you need to have for C or C++ runtime. All low-level programming tools, assembler, linker, disassembler. These tools are available there as well. Different flavors of ISS, so we have a really fast one, a functional one, or you can use also the cycle accurate simulator that is generated by a studio as well. Profiling tools are part of that as well. And last but not least is that we have also the UVM verification generator. So it spits out the classes and everything you need for the verification. You as a user used to have operate the verification environment, but Studio helps you a lot with preparing the environment itself. It helps you with a test generation, because there is a tool by which you can generate the streams of instructions that you added into BK Core. On top of that, there is IDE. It's Eclipse-based IDE that you can operate. It's like a cockpit in which you can use the code itself, clicking on build targets and so on. So that's like the helicopter view or cockpit that you can use. So assuming that you have that, then it's quite a powerful combination, because you don't have to start from scratch. You can use a BK template or BK cores as they are, fully verified, ready to use. And we have customers that are actually using these cores as they are. They don't have to do any modification for their particular application. And we have also customers that prefer to take a BK core as they are and add some differentiation. Differentiation could be the instruction extension, or it can be some microarchitecture enhancements that they, for whatever reason, they did inside of a core. In our case, in this presentation, we will use the combination to explore code density improvements beyond the standard C extension. So why we are talking about the code density? Well, it's really important, especially in the embedded domain. Because if you have a small memory footprint, you can have a small memories, which leads to small power area and so on. So it's really essential to have a really good code density in the embedded domain or deeply embedded domain. Now RISC-V targets it by a C extension. Now C extension is a set of 16-bit instructions. Then some of them can work with the whole register set. Some of them can work with only 8 registers. And this is important because it's tied with the extensions that we did. And most of the C extension works with the integer. There are some loads and stores for floating point extensions, but the main part is for the integer. If you look at the spec, we can find something like that. So we have 8 basic encoding styles, and then I copy and paste the cheat sheet for a C extension, so you can have a list of basic C instructions plus their meaning in the full RVI equivalent. In general, what you can find in the papers, and also it's aligned with our finding, is that using a C extension, you can reduce the size by 20 or 30% depending on the application that you're running. So, but sometimes it's really not enough, and so we try to explore what can be done elsewhere. One thing is that you can look at the compiler and try to use different options that the compiler has to reduce things, to reduce the code size, and that's completely valid. And there was a nice presentation on that given by Western Digital. So that's one way to go. The other way to go is, okay, can we have another instructions that would help with code density? And this is the approach that we choose for this exercise. So it's not about the compiler options necessarily, but also about the instructions that would help with code density. As a test condition, we used one of our cores. We used BK3 with floats, compat instructions, multiply and accumulate, and standard integer set. Then we used our toolchain, which is LLVM based, and we used these flags. We use OZ, which is equivalent to similar as OS in the case of a GCC. And we also implemented the M-safe restore mechanism that's currently in the upstream is missing, as far as I know. So we have this option as well available inside of our LLVM. The M-safe restore is a feature that instead of having, instead of handling stack in each function separately, you have just one place and just call of these functions, which on one hand reduces the code size. On the other hand, the performance is hit by this. But since we are targeting the code size, this option was really necessary. As a benchmark code, we use the standard ones, so Cormac, Drystone, Whetstone, mbench we use as well, mybench, FreeRTOS, and more importantly, since this was driven by customer, we used a customer code as well. Because customer code is real code, it's not benchmarked, right? So it was very important for us. Now we run it, and this is the baseline results. So in our benchmark environment, we got about 53% of instructions that are 32-bit were replaced by 16-bit, which leads to about 27% of code size reduction. Now the table shows the most used ones. By used ones, I mean how often how often the big instruction was replaced by the small one. This is not a big surprise. You have a load, stores, moves, load immediates already. You have on the top list, and on the bottom you have the floating points because not that many benchmarks use a float. So this is something that everyone would kind of expect it. Now, when we look at the code, then we found out several interesting things. And this is what we found out. So I mentioned the floating point already, so it's rarely used. And I'm mentioning it because C extension is quite packed in terms of opcodes. So we decided to, instead of having float instruction in C, we just take the opcodes for another C instructions. You will see that in next slide. We also noticed that there is a lot of memory access operations that requires byte, eventually half. It depends on the application, obviously. But the byte and word are the most common one. Half is sometimes used as well. And we also noticed that the 8-register limitation that the load store instruction have impacts the use of C instruction more than the immediate. Also, we try to use the immediate as a 0, and it's quite interesting what we found out. So the offset is not, the offset doesn't mean, it's not that important as a registers. In the case of branches, we also noticed that there is a lot of equal, not equal, less than, and so on. And we also noticed that there is a huge usage of X0 and the upper part of the 8-bit, the upper part of 8 registers that the C extension can use, so X13, 14, and 15. We also noticed that it's worth it to explore the CLI and CADD with the bigger immediates. So we added a couple of instructions, and this is a list of them. I'm sorry, there's a typo in the semantics, so don't look at that. We just look at the instruction and the operands it has. So basically, we added the store byte, load byte, and stored word and load word, but these two are working with the full set of registers. So it's not limited to 8, but it can be any register that that RISC-V has. And we got about plus 3% additional C instructions. Now, if you look at the half are very dependent on the application. So thanks to the customer code base that we got, the half was reasonably used, so we got another +1. But if we look at the benchmark, like the standard line, like mbench, the number is not that high. But in our testing environment, the floats matter. Another possible improvements are in the branches. So we came up with the C branches, not only the 2 that are available in the C extension already, but we came up with 4 other ones. Basically, what you saw in the previous slide is just recapitulation. So we, as the register operands, we use 8 registers, but this time we replaced X8 with X0 because it's used more often than the low part of F of 8 registers that are in C. And the rest was used by the immediate, in our case 5 bits. And using these branches, we got about +1 additional RISC-V instructions. Now, really interesting thing is that we tried to increase the immediate in the CLI and the CADDI. But we found out that in the case of LLVM, it actually, it didn't end well because the compression ratio decreased in this case. And the reason for that is that LLVM particularly is more sensitive to registers than immediates. And this is aligned with the memory stuff because in the case of a memory, we sacrificed the immediate, and instead of that, we used the full set of registers. So this is aligned with this observation, which means that the LLVM, for whatever reason, is more sensitive to registers. So we just kept the LI and the CADD as it is at the moment without any change. Another experiments we did were experiments with ABI. So in some cases, in some cases, the ABI change can be really significant. So it can lead up to 5% more RISC instructions. We played with the caller save, callee save registers, functional arguments, return values. So we tried to play around with different settings, and we found out that it may improve code size significantly, but there is no golden setting. It really depends on the code. On the application. So the gain can be really nice, but it really depends on the application. So we don't have any the eABI or anything like that at the moment, but thanks to the studio, we are able to play with the different ABI settings to find out the best for the application. So if you put all information together, so there's a table again with a percentage. You can combine that with the table that was presented previously. So, long story short, the memory access gain about 4%, the branches another 1%, ABI advancements can lead to extra 5%, but there's some tweak needed in the ABI. So all in all, you get, if you do addition of these numbers, you get about 10% improvements, which is significant for many applications. I'd like to mention as well that the hardware cost is not that high. It's actually low because it's mainly decoder is influenced. No big hardware was added for these instructions, so the price it's like win-win situation. Now the current C extension is nice, but it can be improved. Now, whether it will be improved or not is up to us as a community, because it's up to us, right? So if we change the C extension in the way that we present it, it can lead into additional saving, say from 53 to, 63. But it means that we have to change the C extension in some way. And this is, a question that we have to solve, a task we have to solve. That's one thing. The second thing is that in the case of a customer use case, we were able to achieve other improvements by instruction fusing, which means that there were some really special DSP instructions that do load, post increment, something addition and multiplication, and then save the result somewhere. So, using this instruction fusion is also beneficial in terms of code size, but it's highly dependent on the application or application domain that we are focusing at. Last but not least is that all of us done thanks to a studio. This is a tool from Codasip, and thanks to the fact that we have a BK3 baseline, that it was quite easy and fast to do iteration to try to find out these instructions that I presented, because we had several iterations per day on the compiler side, because it's just a matter of a couple of minutes to regenerate a C compiler with extensions on that you can design in a studio. And that's all.
How many of those problems you saw can be fixed by a better compiler without changing the C? And for example, if you preload one of the 8 registers with 0, you don't need to use X0 comparisons.
Yeah, that's a good question, and I don't have any bright answer straight ahead. So this is something that we have to explore more, because in this case, we were driven by a customer, so we had to come up with something soon, and this is the output. But again, I think that there is still space in the compiler how we can improve that. Again, there was a nice talk given by WD. So I think that we should explore both options, not only the compiler stuff, but also the C extension itself, because I think that there is a space in both areas.
You mentioned the change on the API. You are considering that it can improve by 5%, right?
Yeah.
So that's what jumped from 5% to 10%, right? But changing the API is not something we can contribute to extend the C extension.
That's correct. That's correct. I know that there is a eAPI ongoing, and the main goal is exactly this. But as I said in the presentation, it can be dangerous, so you have to be careful with that. But it can be a big boost, but we have to be careful. Yeah.
One thing you mentioned was one of the issues with the C extension is that actually it uses a subset of the registers. If you look at if there's a way of optimizing the win structure to select more carefully the registers
Yeah, I think it's connected to the compiler question, like whether we can improve a compiler in a way that it's smart enough to handle the 8 registers more carefully. And I think that there is a space, and it will improve some code density approaches, but I'm not sure that it will gain as much as if you have all registers in place, especially in the LLVM, because as we found out, the LLVM is really sensitive to the registers.